Okay, please.
Okay, this meeting is being recorded. Got it. So thanks for inviting me, and it's a great honor to give a presentation here. And it's really nice to have an in-person talk and a very long format, so we can go into details. And I understand that we have a lot of experts here, so it's really nice to skip away from the 6-minute EG kind of format to you have to hide all the detail, all the equations. But this is really nice. And I would like to acknowledge my collaborators, Jeff Anderson from EnKF and also Levon at NERSC. And also the CIS modeling group, actually. We have several people working on modeling, and that's really helpful to connect to this project. And the project we're working on is trying to use alignment technique in the ensemble filtering framework to improve the forecast of some complex dynamical system, in this particular case, CIs, which is very, very hard to forecast in near term. Okay, so the talk will be divided roughly in 2.5. So the first half is motivation and idea. So where I say, why do we need to care about multi-scale data simulation? Why do we need to use alignment? Second is we stress test our method in the vortex, very simple vortex model, 2D. And in this testing, I explored the several optimization, like how to localize the best way and how to integrate. And there are some assumptions we made in our methodology that's potentially going to deviate in real application, which is problematic. And finally, I will say something about the real implementation and the path forward, the ongoing project, exciting ones. So the first part, motivation. So why do we care about position errors and nonlinearity? So here's a very simple example. I just use a 2D ranking vortex, and what you're seeing here are the constant wind speed contours for each vortex. The black one is a true vortex, it's center of the domain. And the colored lines are different members. I draw these members with only uncertainties in their center location. So the center is spread out from the truth. L spread is the standard deviation of this displacement of these vortices. And the R and W is radius of maximum wind, which is the characteristic size of this vortex. So you can see that when the spread is quite small, the 0.1, it is saying that we have very, very linear errors. So the displacement errors are so small that if you take each point in space, for example, the white plus sign, and draw the error distribution, it's very Gaussian. So in this ideal case, you'll find that the ensemble common filter is really just the optimal solution for this purpose, and it will constrain the analysis very well. However, if you increase the location spread, L spread here, from 0.1 to 3 all the way, and you start to see the distribution becomes non-Gaussian, it's going to be skewed slightly in the middle. And then when the nonlinearity goes too extreme, it will be just non-Gaussian. Yeah. So the ensemble common filter is a linearized method, so it works on Gaussian normal distributions. So this becomes, the analysis becomes suboptimal in this case. Maybe get rid of that. Yeah, because it's hiding too much our view. Yes. So with this motivation, we started formulating data simulation problem with slightly including the displacement errors. So now instead of modeling the prior state XB here, to have only one error component, we think about this having two error components, ED and ER. So ED is displacement error, which is basically say if you have a Q vectors, it's a vector field that tells how much the model grid should be moved to the new location. It's a vector field. XBQ here is, you can think about if I have the vortex in the wrong location, and that moves the vortex around in the domain. So the residual error ER here is basically whatever is left. X star is the truth. So you can think about the sum of the ED and ER is non-linear. So it's hard to say it's drawn from a normal distribution. However, the residual is like you align the vortex already. So whatever remaining is a normal distribution, and the covariance matrix B here is conditioned on these displacement vectors. Now the Bayesian formulation of this data simulation problem becomes more complicated. So instead of posterior and the likelihood multiplied the prior, now you have the likelihood of the observation times the prior but conditioned on the Q, and then multiplied by the distribution of the Q probability. So the cost function is also more complicated, but it's kind of a partitioning problem. So here we have the cost function formulating with respect to both the X and the Q. And the Q are the displacement vectors. It is moving things around. You can think about the XQ to be an aligned or preconditioned set of the prior state. That will pass through the observation operator H to match with the observation Y. So the first term is still the observation mismatch, and the second term is the residual error distribution term, and the fourth and the third and fourth are terms that relate to the displacement. Okay, so the last one, L of Q, is a regularization term for the displacement vectors. So we put here some smoothness constraint. We don't want each individual model state variable to be exactly matching the observation by moving that pixel to whatever location that matches the observation. And we more or less want a smooth vector that push the vicinity all together around. So this L is basically saying we don't want Q to jump around wildly in space. Okay, so this kind of idea was already the first idea come out like similar to this is Ravila et al. 2007, and then later they start working on this, and this is called the feature alignment technique, FAT. They use more or less a two-step solver. The first step is deriving displacement. So you can think about fixing X constant and minimize the cost function with respect to Q first. And then this is a step basically computing the displacement vector or the optical flows that will move things around before you even do data simulation. And the second step is the traditional EnKF update, which is fixing the Q. Given the updated Q, now you minimize for X, minimizing the residual error. Okay, so this is a basic framework. I started thinking about better ways to do this because it's a very nonlinear cost function we're trying to minimize here, and it's very difficult. You think about the topography of this big nonlinear J of X and Q here. There are a lot of local minima because when you can think about when minimizing the J with respect to Q, even you just shift things around a little bit, it's going to change the state drastically. And now your mismatch to the observation changed drastically. You're just switching from one local minima to another. So, but the thing is, if we smooth the whole thing into a large scale component, we just smooth the image. Now the cost function should have a very smooth shape as well. So now it's easier to find the global minimum. So idea is to iterate over scale components from large to small scales, like the outer looping 40 bar. So the large scale iteration is going to help us skip a lot of the local minima before actually refining the resolution. Yeah. So in graphic, I can say that multi-scale alignment works in this way. So here's an example, actually from real examples, the hurricane picture. I'm showing the zonal wind map and filter for 3 different scales. So NS here is the number of scale equals 3. And so the first thing we do is for the large scale, we assimilate the observation to change the prior to the analysis. And you can see that the large scale vortices are behaving nicely, and there are some vectors I plotted here, the actual Q for the large scale. You want to move the vortex closer to the center, right? So this is the result of assimilating observation for the large scale. And now the second step is find this displacement and apply these vectors to move the grid of the model. So by moving the grid, now the medium scale prior is pre-aligned. So now the smaller vortices moving along with the large scale pattern is going to be closer already to the center plus sign. And on top of that aligned prior, we do our medium scale EnKF update and have analysis. And then we do this cycle again. So we find another set of vectors and apply it to the model grid. Here's a 3-scale example, but in theory, you can do this for many. So NS can be 4 or 5 all the way to the Nyquist frequency, right? So if you have a resolution of 100 by 100 model grid points, the most NS here we can set is 25 or 50. And the algorithm I can write down simply by say loop over the S indexing the number of scale. And in each scale loop, I first derive the scale component X n of S, and that is by Fourier or just spectral filtering, Fourier transformation. I can do the same thing for Y, but here I'm using the original Y, so the full resolution observation prior here. The fourth line here, this is the EnKF. You can recognize, I don't need to say too much about it. But here, this line is, you can see, solving for the alignment, the displacement vectors. So these displacement vector solvers are basically fixing the X and trying to minimize the cost function to get Q, right? You can see that we basically have the XA and XB pair here. This is an analysis increment, and the Q actually moves the prior and trying to minimize that residual. And it will be basically say, if I have this analysis increment, how can I move the model mesh so that I can explain the most of the analysis increment by just moving it around. And whatever I cannot explain, it's just maybe changes in the amplitude. It's a residual. And after doing this, I just sum the two contributions. This is a contribution from only the displacement, and this is the residual A minus B, right? The residual errors. Okay. Any questions so far before I move on to the stress testing? Yes, please.
It's not a cost function for Q.
Yes.
I think it was not given, so it sets a displacement error, right?
Mm-hmm.
So it's not given a specific distribution.
Yeah.
Because you in the Bayesian correlation, it has is the distribution of Q.
Please use the microphone.
Yeah. So distribution of Q,
Mm-hmm.
you said it has smoothness constraints.
Yeah, we have.
Which is a kind of regularization, and if it's on log scale, the cost function, it should correspond to like a negative log likelihood, like negative log of the distribution of Q.
It's the Q spatial derivative of the Q's amplitude that are squared, and so the L of Q here is Q differentiated with respect to X and Y, and the magnitude of that. And we have a constant that we can tune to say how much smoothness smoothness is how the vectors like deform, shifts around in the vertical in the horizontal direction. So the underlying assumption of the distribution of the Q is non-informative. I don't think we have a very good assumption whether it should be Gaussian or very flat or distribution. But we just work with using the regularization term to control it, if that makes sense. Any more questions? Do I lose you? Okay. So to stress test the method, I use a very simple model, 2D vortex. So there's a vortex you can see in the central domain, but also some large scale random wind field in background to push it around. And the model is just a vorticity equation with some generation term to make the vortices increase over time. Vorticities increase over time. Here I have 3 bands. The spectrum looks like this, so you can kind of see this is like a typical atmospheric spectrum. So first, second, and third scales, these 3 sum back to the original field. Yes. Okay. If I so first do not run model. Actually, just use 1 cycle and without background flow, just the vortices. And assimilating only 1 observation. The observation is located at the plus sign. I started increasing the number of scales from 1 to 7. So then NS equals 1 is just the original EnKF, right? When I start increasing this more and more multi-scale, you start to see the solution becomes more and more like the particle filter solution. The PF is using importance sampling. So which members closely matched observation will be picked with higher weights and get survived. So this is promising, and the asymptotic behavior is tested with several different scenarios. So first, I use larger space L spread and smaller L spread to have a more quasi-linear regime. So the L over R is 0.2. So this is like the linear regime. So the EnKF is already very good. And then to the right-hand side is the case where it's very, very nonlinear. So these error box plots are summarized from 1,000 trials, and from left to the right. So the leftmost are in gray, and the rightmost are also in gray. These 2 are no DA and PF particle filter solution, and in the middle, these white ones from left to the right are increasing NS. So 1, 2, 3, 4, 5, all the way to 7. And I'm plotting the domain averaged error of this single ranking vortex. Okay. You do see some problem at the linear regime that our multi-scale alignment is slightly degrading the solution over the EnKF, and I'll explain why. So the ranking vortex has a very sharp maximum wind in the peak wind speed. So the wind speed is about 35 meters per second, and the next pixel to that drops already down to 30. So it's a 5 meters per second difference already. So if I have the displacement only like 0.2 grid points, it's going to try to move the peak wind speed to in between the grid points, and my model resolution is not high enough to represent that. So the result is interpolating between the 2 wind speed, and the wind speed actually, the maximum wind speed actually decrease through displacement. And this is causing the additional errors in this plot. Otherwise, it should be also as perfect as the EnKF. And we think this is because of the use of a Eulerian grid. Basically, you need to interpolate. But if you use a Lagrangian grid, you can move the high resolution regions with the sharp gradients around, and then should solve the problem. How about the performance in a cycling DA experiment? So here the model is kind of tuned, so it's going to rapidly intensify the vortex. So we didn't test for steady state behavior because that doesn't really makes a difference. If the vortex doesn't intensify and can't just move around, I think it's less interesting than looking at the transition from a weak to a strong vortex. So I only did 3 cycles every 3 hours, but I do test different realizations of this 12-hour run. I think it's 100 different trials, and I summarized them together, composite averaged them together to show this plot. So first of all, if no DA, then the arrows are growing, both in the domain average sense or also in the position of the vortices sense. And you can see that first, the MSA method in blue, that doesn't really improve over the black, so the traditional single scale EnKF. That is because when we are assimilating, we assimilate the full resolution observation to try to constrain the large scale or each individual scale component. And that's going to introduce a lot of sampling analysis. So I thought how to improve this. So instead, I do this MSA-O, in which when I assimilate or update each scale component, I'm actually filtering the observation to the same scale. So when I try to do the large scale update, I'm also smoothing the observation a little bit to make it a large scale, and then assimilating that. You can see the red lines in the MSA-O here. Actually, it does the best. Remarkably, the position error growth rate, you can see the curve of the red curves. They are like not as steep as the black dashed curve in forecast. So if you have a very good analysis, it should also influence the forecast. It should, there's like memory, right? It should pretend into the future. Also, one thing I'm proud of is the MSA-O outperforms in EnKF, both the analysis and forecast, but also at equal cost. So the line here, you see NS equals 3. You should think that we have increased computational cost because we're doing 3 iterations. But I reduced the ensemble size so that this is actually at equal cost to the single scale EnKF, yet it is still doing better. Okay. But there's an issue with coherence assumption. So we're assuming that, okay, so we have large scale pattern that we compute our analysis increments over, and we use that to solve for the displacement and move the smaller scale patterns around. This assumes that the large scale pattern is in coherence with the small scale. Namely, the background flow is going to be shifted around, and that shifting is going to tell us how the vortices are displaced. However, if the background flow errors and the vortex position errors are out of phase, so in my experiment, I move the background flow to the left while the vortices are actually moved to the right. In that case, the out of phase case will not be improved with the new method, because you think the large scale is moving to one direction and use that direction to move the prior smaller scale vortices. It's going to actually degrade its position error even more before it's a data simulation, right? So you see here on the right, the out of phase case, as the NS increase, it's not going to decrease the error. How often does this deviation from coherence assumption happen? I'm not sure yet. Maybe some of you can give some insight. How frequently in geoscience scientific models we have a large scale feature going on in a model, and actually does totally different things, like statistically uncorrelated with the smaller scale features. I don't know. It's possible, but it's because that's possible that I want to really show this caveat here. Okay, any question related to this testing? I think okay, people are quite.
Can I just ask one quick one?
Yes, Dean.
So what happens, or do you have situations where the vortex in your model is a different size? So the size is different, and then what does it mean to have a displacement field?
So,
and especially when you've got a smoothness constraint.
Yes.
On it.
So Dean asked if I have uncertainties in the size or maybe also amplitude of these vortices in my prior. That will change the problem. Yes. So especially when I have a smoothness to constrain the displacement to be in the large scale. I tested the case when I not only have uncertainty in the position, but also have other sources of uncertainty. That's going to reduce the impact from purely the displacements. And I see the overall effect is MSA gets similar and similar to just single scale. And it's quite consistent. Like as long as you have one small component, let's say 10% of the error that explained by just displacement, the MSA is going to reduce that 10%, and the result is maybe still 90% error residual. But that's going to help, like that. The MSA is not going to magically improve that additional source of error. Yeah. So yes, it is a problem because we're not even sure the nonlinearity caused by displacement is always so dominant in all the application too. Any other questions? Yes.
This is a really, I already phrased it the best possible way. This is going to be a really simple, potentially very dumb question. I was simply thinking on when you talked about the out of phase, in phase. So if you have the smaller scale functions that are moving separately, or that are happening separately from the larger scale. But in that situation, because you only have observations of, like in the way you've set up the system here, that you only have observations from the one but not the other. And in that situation, if you have, now I'm worried if my question will make sense.
No, actually, we don't have observation that's particular for the large scale or the small scale. The observation is always picking up the whole thing.
Yeah. Okay. So this kind then, yeah, because in that situation, can you actually can this system be even theoretically used in that situation? Because you're not actually because if there's no statistical connection there, then the correct transmission. Okay, I stumbled over my question, but
I sort of see your point because the large scale and small scale, you can think about the whole spectrum as one thing. But actually, it's a mixture of several different processes. The large scale physics and small scale physics that's potentially disjoint, but potentially also connected through the cross scale interactions, right?
Yeah.
So you can always think of the case that it's not purely 100% related, also not 0% related. So totally independent. There's always some relationship between the small and large scale. Observation, if you just throw a sensor in the atmosphere, that's going to pick all the scales because it's going to project to it's going to pick up what the large scale flow is. It's also going to pick up the flow related to the vortex if it's near the vortex, right? But the problem is which one is dominant. So when I do the large scale update, actually I want the vortex to dominate in that large scale. I don't want some other flow, maybe near a small island or something, that to be contaminating my large scale update. Here, the out of phase case is just like when you have the situation, the large scale update is contaminated. Yeah, it's one possibility. I think if potentially we can separate different independent modes in the model and do data simulation on each independent mode separately, then we can solve this problem. That's my idea here. So how am I doing on time? Is it like 20 or 30 minutes?
You have you're over 30 minutes.
30 minutes. So I should. It's okay. So a little bit of word on tuning and best localization. This is a kind of practical or technical here. So the localization function we use here is a Gasparian cone with respect to the ROI, which is a radius of influence. This is where the correlations are tapered to 0. And I also, on top of the whole function, I multiply the constant alpha. So I want to be able to dampen the impact from observation if I wish. So here, apologies for the graphic, you see a square, but that should be alpha. So in the vertical direction, alpha is from 0 to 1, and the horizontal direction, larger and larger ROI. I'm plotting constant contours so first let me say this is trying to assimilate observation to update the first scale component. So if I have a larger NS equals what, from 2 to 7. So 7 will be the first scale component of 7 will be very large scale, right? But NS equals 2, the first scale component is almost the same as the full resolution one, so it's smaller scale. So when updating different scale components, what's the best parameters, alpha and ROI here? I did several trials and averaged the root mean square error and plotted the contour where I found within the contour is minimal. So the error is smallest and within 1%. So this is a contour within this area, the parameters you can pick to give it the best performance. So the left-hand side, we are simulating raw observation to update the first scale component. You find that as the scale gets larger and larger, first alpha gets reduced. This is because I'm having a larger and larger scale mismatch between the observation and the model state at large scale. And you also have a little bit shift to the right. So as the scale gets larger and larger, I have larger and larger localization distance that I can use because the underlying physical correlation is getting larger and larger. On the right-hand side, I try to use the filter observation at the corresponding scale to update. I was originally expecting my alpha can be 1 because I have less of a scale mismatch. You do see that the purple line does have some extension from low value alpha to all the way up. But it's also still encouraging the use of larger ROI. But when you use larger ROI here, it's trying to use a lot smaller alpha to compensate for it. Maybe you use a very large ROI and you include more observation to impact the update, and you want to kind of not use fully each individual observation's impact because you use too many observations. Maybe that's the reason. So I hope this figure is clear. Yeah, I don't have anything to say, but I can also, maybe these two are not quite relevant. The other thing, the effect of alpha is 10 minutes, yes. When I observe when my observations are, error models are not good, maybe they are correlated. So from the panel B and C here, you see panel B is what we really assume in EnKF. The observations errors are all uncorrelated, so it's a white noise. But panel C, we have correlation of 0.2 in the spatial direction. So what you see here, observation errors are all in kind of large scale. So when I assimilate that observation, so what I assume here in my model, I will assume the gray dashed line. So these lambdas are the power spectrum of the error covariance matrix. And this is a Lorentz 96 1D case in my 2020 papers. So this is what you assumed in EnKF. So the lower wave number and higher wave numbers are all using the equal density observation error. But the true observation error is actually the black curve. So at large scale, you underestimate the observation error, and at smaller scale, you overestimate the observation error. Okay. As a result, your analysis will have some deficiency at different scale. But what I'm proposing here is to use a multi-scale solution. So at each scale, you can adjust. You can inflate it more or deflate it observation error so that it matches the black curve. And your analysis should be stable. Okay, so finally, I think I've elaborated a lot on the details in the tuning or the inner workings of the MSA. So next thing we're trying to do is to apply it in real application. This is kind of important because we developed DA method of trying to solve real problems. So this problem is particularly challenging. What you see here is the deformation field in the sea ice. Ice, maybe you have the impression that Arctic ice is just a chunk of continuity and sitting on top of the ocean that never really move violently. But if you look at day-to-day scale, you're going to see these features moving around. These ice open up and close due to forcing from top the atmosphere wind flow and ocean current. And on top of that, you have melting and due to high ocean temperatures. And these are quite relevant features for navigation. So we currently don't even have model forecast product for these ice features to provide to the downstream users. So in an effort to make a CIS forecast in this very short scale, the CIS modeling group attempt to assimilate deformation observation, but the approach they use right now is very not advanced. It's still using linear combination. So whenever we observe the deformation Y here, we kind of retrieve the corresponding CIS concentration with a linear dependency. So here's a reconstruction of observed CIS concentration due to deformation on the X direction, and on the Y direction is the actual modeled CIS concentration. We hope that we see a one-to-one relationship between the two, but actually it's not quite. But we still use that to change our model CIS concentration with the information here. And it's still going to decrease some error, and the error will increase back in the forecast, and that this buy us some extra forecast lead hours, maybe a lead time in terms of 2 days or 3 days, but it's not optimal. So here's an example of this assimilation scheme, current simplified assimilation scheme. You see that whenever observations are available, you're gonna just change the value there, and if the value changes, shift around, and kind of gets forgotten by the model very rapidly. This is because of the physical inconsistency between the atmosphere ocean interface. Whenever you change the CIs, you don't change the atmosphere and ocean around it. So it's going to maybe not live very long. Okay, and I'm proposing the next step is trying to use the MSA. So you can see from this pyramid view that we are moving the large scale ice around and then hoping that the deformation or the cracks are going to be aligned better. And then we do data simulation and align, and simulation and align. So at NERSC, we have this the next generation CIS model. And we are using also on top of that, the TOPAZ system, which is based on a HICOM ocean model. We do have some atmospheric modeling, but not so much on the data simulation side. I am thinking if we can, in the future, not really right now because we don't have the right software, but in the future, if we can do a simulation on all three components and make consistent analysis update, especially the alignment is going to move around the whole column. So it's going to be physically consistent. That would be really nice. But right now we have some software challenge because currently there are many versions of EnKF code existing in our center, and we don't know how to best utilize the old versions. And I'm thinking of modularizing the system so that we can swap in and out different components. Yeah. So finally, okay. I think I can summarize by saying position error is a very big chunk of nonlinearity in our field, and it's all really everywhere. Sometimes causing nonlinearity that's not necessarily the hard kind of nonlinearity, but it's causing deficiency in scale. So we can solve this by simply using a multi-scale alignment technique. We have tested the methods thoroughly in simplified situations, but now we're looking forward to real implementation, and that's important in the future. Here are 2 papers that are currently in review related to talk. Yeah, thank you.
Into the computer. Thank you, Michael. So you started a bit late, so I will allow for a question. I did not see any in the chat, so but here comes one from Patrick, and I guess we should repeat the question to the online.
Yes, I will.
Yeah.
Okay.
All right, so I got a few questions actually, so just to stop me, please. Anybody else? So could you comment on your work from the perspective of state augmentation in general to include more parameters. And from the perspective of what was it?
Do you mean parameters in the model?
How to choose the parameterization of your state as well.
So the
You
question,
chose displacement, right? Because some other kind of transformation of.
okay, so Patrick asked a question about my choice of using displacement vectors as an augmentation of the model state vector. I need to think about. I don't really see this displacement vector Q as actually additional parameters to the state, because they are actually the coordinates. The uncertainties in the coordinate of the state. You can think about a model state X here to be a nonlinear function of the coordinates X and Y. So X and Y is already taken by the DA formulation. But anyway, these are, so let's say R is the horizontal coordinate, and Q here is just maybe a representation of the coordinate uncertainty. So this is not adding things to the state vector to me. It's like transforming the X to Q in a sense. Any other? You have more?
Just a follow-up. When you say transform the coordinates,
yeah.
Do you just have a simple displacement shift, or do you really, like in the Jacobian, you dilate and squeeze is that killer field, or just one coordinate that you move around?
I do have ensemble system. So if I move each individual members separately in different, so the Qs are specific for each members. So that will effectively, let me see. So these vectors, I'm showing one member. Okay, so these vectors are different for each member.
Right.
So Q have an ensemble of Qs. So
I don't. For each member, you only have two coordinates, two
coordinates.
Yeah, two. Yeah. So the whole thing has to move, not every.
Not for each different pixel. You see, the flow field is not a constant flow. It's a flow field. So,
okay.
So it's going to have some spatial variation.
Okay.
Yes. Yeah.
Thank you.
Actually, now I think we should move on, and you can either write more of your questions in the chat, but then you have to say who it is for, or we also have this Slack, right, Shana?
Yeah.
But chat is also okay.
Yeah.
So and of course in the break and lunch and dinner. So thanks a lot.
Yeah.
Thanks again to Michael. Then we move on to the next speaker. The next speaker is online. So let's see, Jeffrey de Montle-Basidek.
Yes.
Hopefully that's not too wrong. Are you there?
I'm there.
Yes.
Do you hear me?
I can see you, but we cannot hear you. Maybe I have to unmute you.
Okay, no, I'm on mute, but I will. Okay.
Yeah, but we cannot hear him.
Do you hear me now?
Okay, so it appears that online they can hear Jeffrey.
Okay,
but Sheldon? Yeah.
Check the arrow.
Yes.
Mute. So
Yeah. The point is that yeah.
Are you using? Not yet. The arrow next to the microphone.
Yeah.
The arrow next to the, so yeah, you
I
will
will
see
move.
yeah, we are using the speaker of Sony something.
You
No.
hear me now?
Could you couple up with something like for the speakers in the room?
I have no idea.
Hello. So someone online can confirm that they hear me? Okay, thank you.
Is this going to work? Okay. Try to say something, Jeffrey.
Yes, I'm speaking now, but I think you do not hear me.
Now we can hear.
Speaker.
It's good enough?
No, I think, yeah, maybe they have to use microphone.
Okay.
Yeah, can you say something?
Yes, do you hear me? No, you don't hear me?
Yeah, we do hear you. It was just to get the sound out to the screen.
Okay.
Out to the audience here. Okay, just please go ahead and share your screen.
Yes.
Yes.
So you see my screen now? Everything is fine?
Yeah, it's just that still no. Do you still not hear, right?
I don't know me. I hear you, but I think you do not.
No, no, I was talking to the audience. I'm sorry.
Those who have computer, maybe they can hear, but then the sound system here is a bit strange because it's not connected. Yes, it's not connected.
Yeah. Okay, but I think we just have to.
I need to find the support.
Yeah, so we have a problem here in the room because we are not connected to the speakers. I suggest we have our coffee break now. We have one break now for 5 minutes. 5-minute break before we come back. I'm not because we need to connect this speakers.
This one is maximum.
Så dette, ja, sånn er det dag 1. Skal vi se. Har den makt, men det må jo hende det kommer ut, og det burde jo bare holde denne inntil.
Ja, det er en dårlig løsning. Det er absolutt ikke anbefalt. Du får masse Hvis vi kommer inn og ut, så er det bare ikke inne her.
Det er ikke sikkert det er, men det må jo være høyttaler.
Det må være en måte å få litt sterkere.
I would hope that the technical staff.
Ja, vi hadde møte med han i dag tidlig, men kanskje vi glemte å spørre om akkurat dette. Nå er det første foredrag som skal
Men da må vi bare prøve å ta inn og ut.
Men hva er det egentlig, se her, hva er det egentlig han skal stå på? Speakers, er det Realtek, Sony PJ, same as system? Okay. Jeffrey, are you still there?
Yeah, I'm there.
Jeffrey, can you try to say something?
Yes, now I'm here and I'm trying to say something.
Oh, he's talking, but no, okay, we cannot hear you. So how? Sony, we are testing Sony PJ. Okay, say hello now.
Hello, I'm Geoffrey. Complex releases through inverse modeling methods. So it's a work we developed at the IRSN, the Radio Protection Center of France, with Olivier Saunier, and CEREA, the Laboratory of Atmospheric Dispersion, with Marc Boquet and Yelva Roustan. And so more precisely, we'll talk about uncertainty quantification methods for radionuclides release, so radioactive particle release, and about the accident of Fukushima Daiichi. So just a small reminder, in March 2011, there was an earthquake under the Pacific Ocean off the coast of Japan, and this earthquake triggered an extremely destructive tsunami that hit the Japanese coastline 1 hour after the beginning of the earthquake. This resulted in the drowning of the emergency power generators of the Fukushima Daiichi central, which led to a massive release of radionuclides, such as, for example, the cesium-137, which will be the radionuclide of interest today. And this release was characterized by several episodes of varying intensity and lasted for several weeks. So the estimation of such a release is difficult, is subject to significant uncertainties. It's a highly variable release running over several hundreds of hours. And so our objective is to reconstruct this release with inverse modeling method. So as you may know, in the inverse modeling framework, we need two things. We need observations and we need a model. So the observations we will use here will be both air concentration measurements and deposition measurements. So a lot more measurements between the 11th of March and deposition measurements, a transport model, of course, and it will be an Eulerian transport model, the one of IRSN, which will be represented by a linear observation operator H. This model needs meteorological data to run, and we use data from the ECMWF. So with the observations Y and the transport model H defined, we can build the inverse problem, which is based on the observation equation, which is written here. So it's just basically the equations which links an observations vector Y with predictions vector Hx, and the predictions vector is a result of the multiplication of the observation operator, so the atmospheric transport model, with the source. So the source vector describing the source of the releases. Just a note, H is representing the radionuclide transportation for a unitary source. So there is an important hypothesis of linearity. And finally, since of course there are differences between the observations and the predictions of the model, we have a term which is the observation error, epsilon. So all variables which are describing the source of the release, such as the height or the coordinates, will be assumed to be known, except for one thing, the source term, of course. So the evolution of the release of cesium from the Fukushima Daiichi plant, which we describe with a vector of constant release rates of a certain size. The size is the number of pulses that we consider, but there is a problem. How do we choose the size of each pulse? How do we choose the number of pulses? basically, how do we choose each step of the Q vector representing the release? So this is more generally the problem of the representation of a continuous release by a step function. The problem is the following. We have a complex continuous release function, which is a green curve, and we want to model this green curve with a discrete step function. So here it's the red curve. The question is how to find the best discrete function to represent it. We don't want too many steps so as to not overfit the observations and for reasons of computing power. And we don't want too few steps because it would mean too many hypotheses on the model and the model not complex enough to learn from the information at our disposal. The questions are, what is the right number of steps and what is the correct side of each step? It's basically the famous bias variance trade-off between bias, error of a too simple model, and variance, overfitting or overinterpretation of the data. So an idea to solve this trade-off is to notice that if we can inverse the source, we might also be able to inverse the parametrization of the source. And a natural way to do so is to use a Bayesian formalism. And before to introduce the method that we will use, we introduce the Bayesian formalism that we use. So we have defined the inverse modeling problem from the observation equation. And the Bayesian inverse modeling is simply an adaptation of this with a Bayes formula. So as you know, it's just a description of the posterior distribution that we want to reconstruct. So the distribution of the source given some data according to two distributions, the likelihood, which is a diagnostic of the differences between the observations and the predictions, and the prior, which is our information on the source before having access to any kind of data. So just a note now, we are adding to the source, the variable that we want to reconstruct. We are adding to the release rates Q, the observation error scale matrix R, which is the scale matrix of the likelihood, and the source prior scale matrix B, which will be the covariance matrix from the prior on the release rates. So now that we have our definition of the distribution that we want to reconstruct, we need to solve two problems. We need to define distributions, and we need to define a sampler to reconstruct this distribution. For this sampler, a basic idea, a popular idea is to use the popular NCMC algorithm, the Metropolis-Hastings algorithm. So how does it work? It's essentially a procedure where a Markov chain states that only depends on the previous state work towards high probability spaces. It's a procedure of rigorous sampling of a distribution in basically three steps. There is on the left here a proposal step where a new source is proposed. There in the middle an acceptation rate calculation step where we compute the probability of the new source proposed compared to the old one. And there is finally an accept or reject step where we accept or reject these new candidates. So this algorithm works very fine for problems where variables have a fixed size, so monodimensional problems, but does not work for our problem where we want the dimension of the variable to evolve to find their most probable representations, so transdimensional problems. So we need an extension of this Metropolis-Hastings to transdimensional problems, and we present in the next slide more specifically the motive of this extension by specifying how exactly our variables are transdimensional. So here you have a figure, and on this figure you have 6 Qi, which are basically release rates. So it's our vector of constant release rates Q, and we can the goal is to find this Q, but also the good representation of Q. We can note that these constant release rates are separated by edges, the lambda I, and so the evolution of the release is totally modeled by a specific partition of edges. An idea is simply to note that we can add this set of edges to the NCMC procedure, so we can add it in the vector X that we want to reconstruct. We want to reconstruct the distribution of X given the data. The problem is that when we change the set of edges, we change the dimensions of the problem. And of course, this adds a lot of complications. And this is where we need to adapt the Metropolis-Hastings algorithm. And we will use what is called the reversible jump MCMC algorithm. So basically, the reversible jump is another MCMC, another layer on the Metropolis-Hastings algorithm, but with modifications on the walk and acceptation rate steps. So the two first steps of the Metropolis-Hastings algorithm. Basically, we will add to the classic Metropolis-Hastings walks, we will add trans-dimensional walk. So here you have an example of such a walk. A walk is here is the birth procedure. We create an edge and we go from dimension n to dimension n+1. And you can note also that we create a release rate in the process. So we had 2 release rates and 3 edges, and now we have 3 release rates and 4 edges. So the acceptation rate is also modified afterwards to ensure the detailed balance. So basically, the detailed balance in the MCMC is the reversibility of the transitions of the Markov chains, and the reason why MCMC converge to the distributions. This also leads to redefinitions of the priors and to new definitions of the transitions on the variables and release rates. We need to define our edge transition, our death transition, etc. But our birth and death transitions, our etc. So yes, what is nice here is that we can note that the reversible jump MCMC will be able to make a lot of use of a lot of precise and diverse information, because it's able to reconstruct not only the release, but also the representation of the release. So we describe in the next slide which kind of information we use and how we integrate these informations in the Bayesian inverse problem by simply redefining the observation error scale matrix. So we are interested in 2 types of informations. Here, one way will be to factor both concentration and deposition measurements into a Bayesian sampling. So we will combine diverse types of measurements. And another one will be that we will take into account spatial distances between air concentration measurements. And these heterogeneous informations will be simply assessed in the scale likelihood matrix by making clusters of similar observations. So for example, we consider that all deposition measurements are similar, and we use one hyperparameter, RD, for all deposition measurements. And so this modifies the vector that we want to sample now. It's not only the vector of release rates. We use actually the logarithm of the vector of release rates, which is transdimensional. We have a certain number of clusters of spatial clusters of air concentration measurements, one cluster of deposition measurements, one hyperparameter corresponding to the cluster of deposition measurements, and a certain number of edges, which is also transdimensional. Okay, so now we have our methods, but we do not have yet the definitions of the distributions that we use in the Bayesian definitions. And so we will describe it now. So for the likelihood, we use a log-Cauchy distribution, which has this scale matrix R. So here is the description of the log-Cauchy distribution. It's very efficient to manage observations of diverse orders of magnitude. And to manage the observations close to 0, we add a threshold term, YT. For what concerns the priors, we use uniform priors on the scale parameters, and we use exponential priors on the edges to penalize 2 complex models. So here you see which kind of exponential prior it is. For the prior on the release rates, it is more complicated, more tricky. We use a folded Gaussian prior with a B covariance matrix, which is parameterized by 2 hyperparameters. One of them is used for pulses that are constrained by the observations, and the other for pulses not constrained by the observations. and we only sample the BC here, the hyperparameter, which is associated to the pulses constrained by the observations. We can note that this prior also constrains the model complexity. And finally, now that we have defined our distributions, we have the vector that we want to sample fully defined, and we have our method of sampling. We can apply these methods to the reconstruction of the Fukushima Daiichi cesium release source. So here we propose a complete representation of the cesium release evolution. So the red curve, the hard line is our reconstruction. It's basically the median of the distribution that we reconstruct. And the red shading is the median plus or minus the standard deviation. And it is compared to two other source terms, the one of Saunier in 2013 and the one of Terada in 2020 in green and blue. We can note diverse things. There are intervals of high variability, for example, between the 14th and the 15th. There are intervals of low variability, for example, between the 11th and the 14th. There is a large variability of the variability. And this basically proves the reversible jump and CMC pertinence. The use of more information and more complex algorithms allows us to reconstruct a complex release with several release episodes. Here we reconstruct the average number of sampled edges at each time and the associated standard deviation. So in essence, this curve shows the number of edges necessary to model the release at a certain time. So it's basically the variability of the release according to the algorithm. And we can note diverse things. There is again a large variability between the 14th and the 15th, and between the 19th and the 21st. So this observation confirms once again the relevance of using the reversible jump and CMC algorithm. There are periods of high variability which can be sampled finely. And finally, here we reconstruct, we study the interest of adding these deposition measurements by looking at the distributions of the total release. And we can see again that there is interest to use diverse types of measurements because this addition of deposition measurements will modify the distribution. It will increase the uncertainty, provide other modes. The total release will be assumed to be higher in average, etc. So to summarize, from the beginning, we saw that complex releases implied nonetheless a high variability, but also a high variability of the variability. The modeling of such a release is complicated to define because there might be at some periods too simple, which will imply bias errors. It might be at some periods too complicated, which would imply overfitting plus variance error. And so the use of this reversible jump MCMC allows us to reconstruct the best model by solving the bias variance trade-off, and thus to better estimate the uncertainties related to the release representation. So as a conclusion, the addition of information and the better exploitation of this information is helping us to reconstruct a more complex and fine-grained release. And we will propose soon to ACP a paper summarizing our work. Thank you for your time. Thank you.
Yeah, Jeffrey, they were clapping, so I was just not fast enough to unmute us. So yes, we have time for questions. So first, the audience, we have one over here, yes.
Hello, I didn't understand how you take spatial distance between observations into account in your art matrix.
Okay, I have to repeat, remember. So yeah. Oh, do you hear? Do you hear this?
I think I heard the questions. How do we take into account the spatial distances? So it's simply a k-means clustering on the observations to make clusters of observations depending on their spatial distances, the corresponding spatial distances. And we use in these applications, we use 9 9 clusters, so 9 clusters depending on their spatial distances. We also did this work for spatio-temporal distances because observations are at different times, but it's described in the paper that we will want to publish sooner.
But you're showing a diagonal matrix, which means that the diagonal elements are just both the variance for itself is not there's why your all diagonal elements are 0. I mean, that means the correlation between 2 different points, between the observation at 2 different points in spatial space. That means if you take the distance that they will not be 0 elements, right?
I'm sorry, you mean that the covariance
why they are 0?
So why we use a diagonal matrix, because basically it's since we want to sample these parameters, and since we have now with every measurement we have more than 15,000 observations, and so this matrix would be 15,000 multiplied by 15,000 parameters, and in an NCNC it's far too many parameters. It's not possible to sample more than I don't know 50 millions of parameters. So here we have only something like 100 or 200 parameters depending on the dimensions of this, and I think it's how can I say, it's kind of a maximum that we can what we can sample with an NCNC. So to simplify the problem, since we want to reconstruct these uncertainties with we want to sample their distributions with an NCNC, we need to make huge simplifications. So we define that it is a diagonal matrix, and we try to also to reduce the number of parameters on the diagonal in order not to have 15,000 diagonal parameters.
Okay, thank you.
Yeah, thank you. And we have time for one more question. We have time for more questions, actually.
Nothing from online.
Nothing from online. Okay.
No, I think we can just move on.
Yeah, we will
skip the break time.
Yeah.
So to catch up the session.
That's good. Then we move on. Thank you, Jeffrey.
Thank you.
So then, Adil Siripatana, are you ready to share your presentation?
Hi, can you hear me?
Yes, we can hear you.
Yeah. Let me share my screen. What's that?
Yeah.
Wait. Okay, let me try sharing my desktop maybe.
Oh, that's fine.
Okay, Zoom. My computer have some privacy issues, I think. I'll share again.
Yeah, we have had issues here today, so just relax and try to find the right button.
Sorry, I didn't expect this. Microsoft Teams. Share. Okay. Unlocking. Okay, Zoom now allow. Okay. Oh no. Can I leave and come back? Maybe it work if I leave.
Oh, okay, we will have a very short break then. Yes, go grab a coffee. We will call you in when we are ready. What? Oh, yeah, but we never know.
Okay. I think that work.
Okay, let's see.
Sorry.
Now we can see your screen.
I
Yeah,
think we can just move on. Start the
yeah.
presentation.
Yeah.
Can you,
But
can you
Shadong,
hear
will
me?
you tell them that we are starting, but they can come, be quiet when they come in? Yes, let's see. Now we see the full screen, yes. And that looks good.
Yeah.
So then I will mute my microphone from here, and you have 30 minutes from now. So please just go ahead, Adil.
All right. So let me. Thank you very much. Sorry, okay, I can start. It's fine if you guys cannot see me. Thanks. Can you hear me? Sorry. Okay.
Yes, we can hear you and we can see the presentation. So
Okay,
yeah, we don't see you, but that's okay. I think.
All right. Sorry.
Yeah.
So thank you, everyone. My name is Adil, and I'm working with the CREAD group, which stands for Space Environment and Radio Engineering at the University of Birmingham. Today, I will be talking in the topic, namely incorporating correlate observation error statistic in the upper atmospheric ensemble data simulative model. I want to give thanks to Sean Elwish and David Siemens. They are my colleague, and they give a lot of materials regarding the space environment. So as you can see here, space environment is very crucial for our worldly activities. Normally, we use the space environment that have a lot of electron content for our communication and geolocation, and also GNSS things. And also in the outer space, if there is an extreme space event, it can cause and harm the astronaut and even destroy the satellite. And so to simulate the space environment accurately is very crucial. And data simulation will take part in that as well. For example, not so long ago, you might hear the news that the SpaceX has lost about 40 satellites just because there is a space storm, the solar storm that they are not aware of. And because of that, now SpaceX is looking to find a product of the upper atmosphere that gives them the good prediction of this thing, so they can at least shut down the satellite before the event happen. And also there is a discussion regarding what will happen if we have very severe space storm, how the infrastructure on Earth that related to internet will perform, and how can we prevent that thing from happening? How can we prevent the severe result from that? So what we'll be talking today is going to be about the ionosphere. So the ionosphere is the layer of the atmosphere which has the altitude from 80 kilometers to 1,000 kilometers, sorry. And this is the area where the electromagnetic waves from the sun collide and photons ionize with atmosphere constituents. And this create a free electron and also positive charge molecules in this area. And it's highly coupled to the magnetic field. So any disturbance in the magnetic field will also make create the irregularity in the electron density, especially as well. And if you look at the figure on the right, you can see that there is many, if you look at the cross section or the profile of the electron density against the altitude, you can see that at around 200 to 300, there is the maximum electron density, which we call F2 region. This is the region where they use to bounce the signal, the communication signal, which is a radio signal from place to place, and it can cover the area like 3,000 kilometers. And the condition of this area, F1, F2 area, always change, depend on the season, we depend on time, either it's nighttime or daytime. Normally daytime, we will have a very strong variability and a lot of electron density. So it's worth reminding that the ionosphere is embedded in the thermosphere. So what happened is that the electromagnetic field hit the gas in the thermosphere, and then photoionization create the electron density, and then it's come in the form of free electron and NO plus and also oxygen plus. So mainly the gas that occupy this area going to be oxygen and nitrogen, and also we have different constitution as well, but that not a lot of that. And at night there will be the recombination of this positive charge, and then we create more of the neutral molecule at night, and we have less electron at night. So let's talk about the driver of the ionosphere. If we look at the variability of the ionosphere, looking at different index, something like F10.7. F10.7 is the index that indicate the solar flux, which is correlate very strongly with the ultraviolet waves, and so it's correlate very much with the photoionization. If you look at the time, you will see that the F10.7 have a time scale or have the cycle of about 11 years, which is also similar to the sunspot cycle. The maximum will happen every 11 years. If you look down here in the black figure here, you also have the driver called KP and the sunspot, and you can see that they are quite correlated. The KP is the geomagnetic disturbance index. It indicates how geomagnetic field of the Earth is being disturbed. The more disturbed it is, the more variability or more irregularity will happen in the atmosphere. So the ionosphere will become more dynamics. I also show here the median term variability as well, meaning that even in the same month, each day we will have the different range of the electron, total electron density, total electron content, I would say. Yeah. You can also look at the specific time, and then you can look at the spatial time scale, spatial variability. For example, when the geomagnetic field is quite disturbed, there will be auroral activities near 70 degree north. And normally we will also have equatorial anomaly, which happen because we have a lot of sun energy in this area. So the variability is more in this area. So like I said before, the structure of the ionosphere highly affect the activities that we human do. For example, if you send the signal from the satellite to the receiver down to the ground, the irregularity can cause what we call scintillation, which will bend the ray and then delay and also give us a noisy signal. And even in the moderate condition, the delay in the radio signal can also give us the error in the ranging of the distance and give us the incorrect range, between the satellite and the receiver. And also in the F region where we use for the radar communication, if we incorrectly specify the electron density content in that area, we will most likely have the incorrect maximum frequency that we can use for that purpose, and it's not good. We can lose some signal. So yeah, of course we can have different model to predict the ionosphere. We have statistical model, physics-based model based on the first principle, and of course we can add data simulation to that. And as Serene Group, we did all that. Each of us do different things, but we use this model operationally right now in UK and in European area and in North America as well. So the model that we use as a background is called High GCM. It's developed by the EnKF, of course, and it can accommodate the resolution of 2.5 to 5.0 degree. And the height of this model is from 90 to 600 kilometers. And we have like 16 variables for each node. So you can imagine that as we increase the node, the state vector is going to be quite large, and performing data simulation in this space is going to be quite expensive. So I hope you can see the title here. Yeah. So the model we call NS, and it's data simulation code. It's a 4D modular design based on Python code, and it can be used with, can be paired with any background model, and it's accommodate atmosphere and ionosphere. And the aim for this model was to nowcast and forecast the ionosphere state for 12 hours accurately, and it's useful for radio frequency system and orbit conjunction analysis. And the basics of the NS is the local ensemble command filter. The reason that we design the NS using local ensemble command filter is that it's done everything in the ensemble space. So fewer ensemble member is required compared to EnKF. And doing local analysis in ETKF will restrict the spurious long range correlation as well. So this is just a cartoon of what the localization look like. And of course, I just want to put it out here that EnKF's local ETKF scale as the cube of number of ensemble members, while EnKF scale with the cube of number of observations. So this is just a choice that we choose for our future application, so we can do a lot of parallelizations, and we don't require a huge number of ensemble members. Also, how do we generate the ensembles members? We simply just varies the driver that I mentioned before, like F10.7, cross-tail potential and atmospheric power, which is actually derived from the KP index. And so you can see that on the right-hand side, the figure, you can see the electron density as a function of altitude for 32 members. It's going to look like this. If it's a video, it can collapse as well if you don't do correct assimilation. So what data are we assimilating? What we assimilating called total electron content, which is not the point-wise measurement or the direct measurement, but rather the line integral measurement of the electron density. So basically, if we have the satellite and the receiver, the tech is the integral values from the satellite to the receiver on the path of the ray. And the plot on the left-hand side is basically just the vertical component of the tech. So we can plot them from the top viewpoint. So you can see that we have very good coverage, but most of the data are on land and only some on the island and on the north. on the North Pole, on the South Pole. This is just an example of the ensemble mean or the analysis that we made by using NS. This is from 2017 in the middle of the year and also in the middle of the day. And you can see that where we have large tech, that means that we have a lot of sun, and also we also have a lot of observation as well. In the north, the tech is lower, and in the south, the very south, the tech also very low because we have less sun, and also we don't have a lot of observations. Also, you can see in the ocean, we have not done very well to recover that area. All right, so just to wrap up before we move on, we just have ETKF in the NS is highly parallel. Fewer ensemble members required compared to EnKF, and is a probabilistics radio frequency tool. It can accommodate different observation in the future as well. And in the long term, we can use this to predict the satellite drag. And you can read more from the paper that I show here. All right, so what could be the issue now? Right now, the tech observation that we use for the assimilation is quite sparse, but in the future, we will have more high rate observation, such as the radio occultation, and that shoot from satellite to satellite, and is much more frequent. And in that case, the assumption by NS that the observation covariance is diagonal, not gonna hold anymore. So we have to come up with a way to represent better the observation covariance matrix. So we can use two methods. Basically, the idea is that we can use the analysis innovation and background innovation, and we can compute that, can approximate the observation error covariance matrix, or we can downsampling the data. But that had to be done in a very smart way to minimize the information loss. And in this work, we will talk about estimating the full observation covariance matrix. Doing this, we can reduce the analysis error. We can improve forecast skill. We can inject small scale information to the analysis as well. And we can allow better use of available information. So the method that we use is called DBCP diagnostic, which is described by Desrosier in 2005. The idea is if in the perfect system, the observation covariance matrix can be approximate using the expectation of the product of the innovation analysis innovation and the background innovation transpose. So here this is a simple, there's many assumptions that this will work, but in the past, people also try this in the more idealized setting and also in the chaotic system. For example, for a Waller paper in 2014, they present the schematic or the method, how to apply this in the operational system or real-time system. So most of the steps are the same as the ETKF. Oh, I have to note here that to do this, we don't use the local ETKF, but instead we only use ETKF because the local ETKF is still quite, when we use this method in the LETKF, they break the assumption that we cannot break. So this method is quite limited to the ETKF. So the first two steps is the same as ETKF. We propagate the ensemble member using full nonlinear model. Then we calculate background ensemble mean and background covariance. And from this, we can calculate the background innovation in step 3. After that, in step 4, we can calculate the gain and the analysis, the mean analysis. And on step 5, we can then calculate the analysis innovation. On step 6, so for every analysis time step, we record this innovation and we multiply them together according to the formula I give before. And then we can do the average over time. This will give us the both spatial and temporal correlation or covariance. And you can take as many samples as you want. So you can go back to the previous assimilation step and take as many as you want until you think it's fit or is converged to the correct correct R. Of course, you have to symmetrize the metrics and also reconditioning it as well if you want it to work normally. All right. So we have some challenge though. This method works well in the idealized setting before, where we assume that the observations are quite regular in space. And so we don't have we should have this different number of observation, but this is not going to be true in the operational setting. For example, here we have the satellite, the same satellite and receiver. And for some time step, we might have the geometry or we have some obstruction of the signal that will not allow that observation to be recorded. So you not only have the different geometry because the satellite moving, but you also have different number of observation. And when this happens, we need to think a little bit about how do we characterize the observation. How do we count what thing is the observation? Do we count the thing that are at the same place, or do we look at the satellite separately, pairs separately, and that's what we come up with. So basically, you just need to think of the satellite and receiver pair as one instrument. So for each pair, you have one observation, and you know that between the different pair of satellite and the receiver, there will be some correlation between them, or the covariance or the variance, you know. And this does not depend on the location of the satellite. So you can just create the global matrix of all the possible pairs of the satellite and the receiver. Here I give the name SR1, and then SR1, SR2, SR1, SR3, and so on and so on. And for each time step, sometimes you will have some values according to those pairs, you know, and as in some array of the R, you might have none because you don't have enough information. But this array is global, so it contains all possible pair. Then you can just increase the time step in the assimilation, and then you can record this value. And then at the end, if you have enough sample, if you think you have enough sample, you can take the average, do something like non-mean in Python, for example, to obtain the full R array, or the matrix. You can also change it to the matrix, of course. So I just want to show the primary learning result that we have by doing that. So on the left-hand side, I plot the error between the analysis and the direct observation, which is the independent observation. We get the observation of the electron density from the swarm satellite. Then we just do root mean square error over 12 hours. And we look at the plot. So the black line is the EnKF with the diagnostic. So as you increase the number of ensemble size, you can see that it's kind of converged to the EnKF. Not quite beat the EnKF yet. It beat EnKF for some height, some altitude, but not all altitude. And it still performed poorly compared to the LETKF. This is quite promising, but we know that somehow we still have not well approximate the R matrix. So we look at the R matrix from on the right. The top one is the diagonal matrix we start with when we start the assimilation, and then the bottom one is the estimate R when we estimate the assimilate the data for Y. So we can see that the structure is quite different, and also the covariance is also quite different. I mean, it seems to us that the assimilation system kind of ignore this the large structure because it doesn't help the filter that well, and so it's kind of still think that the data is independent. So we have not done very good job at representing the R. So now it's very difficult to find the optimize this problem because we have a lot of factors in our NS model. So we start we step back a little bit and look at the toy model where we can control everything, and we will study the behavior of this system before we get the idea what to do next. So we have the bouncing ball problem, where we have initial condition, the ball drop from some height and then they bounce. We have the truth, and then we have the observation that we create from perturbing the truth. And then we do the same thing. We do the diagnostic with EnKF, and we have the analysis assemble. Then we look at, and we assume that we have we record five observations: height, mass, radius, air, density, and viscosity. And then we look at the estimate and true R, and they look quite similar. The structure is the same, only the range of the covariance is a little bit different. So here we prove that the system works, and we can use this as our reference before we move on. And we also look at the different sample size. We plot the error according to the sample size and observation step. And we found that if we use the small observation step, they're going to be issue. They're going to be large error. We just need to increase the observation step, and it doesn't matter how many sample size we use, we're going to get low error. So the idea here is that we should increase the number or the spin up period in our model. Right now we run this model for only 1 day. We might need to increase it to 6 to 1 week to get something close to this. So yeah, that is the current work that we are working on. And in conclusion, right now we have the EnKF type data simulation model for ionosphere, and as Syrian we developed NS, and this is based on LETKF. Right now we developing the full observation error covariance matrix estimation functionality in NS to accommodate future high rate observation, and there's still room to improve. And the toy problem indicate that we just need longer spin up period and maybe longer spin up for the diagnostic as well. Thank you.
Thanks a lot. Thank you, Adil. And yeah, we have 2 minutes. So I'm opening.
Sorry, now video is back. Sorry.
Yes, I'm opening for one question. Yes, we have one from the audience here.
Laurent Matelot speaking. I'd like to know if you've considered clustering in the ensemble, because you spend really a lot of efforts on the observations clustering, which, well, I thought was handled already by EnKF. But when you showed your ensemble on one slide with the profiles, it looked like you had a lot of members on the same line and a few off the group. Isn't that, something you would like to sub-sample?
Yeah. I actually agree. Actually, we are doing the poor job, initialize the ensemble. Like I mentioned before, if we leave the assimilation goes for a while, the ensembles usually collapse very fast. I mean, the assimilation and the model itself right now is perform poorly, and we now trying to find a way to parameterize the F10.7 better. Right now we look back and we take like 80 days sample, and then we assume Gaussian, and then we sample from that. But right now we also look at different way to sample that for the F10.7, and that is still in the discussion. Maybe I hope I answer your question.
Yes, thank you.
Yeah.
Yes. Yes, thank you. So then we actually have to move on, but there can be more discussion in the chat. And according to the program, we are scheduled for a 15-minute break. That will not happen. We will have 5-minute break. Be back 10:10. No, 11:10. 11:10. So Patrick Laloyos.
Can you hear me?
You wanna start preparing, sharing,
Okay,
and
cool. Yeah, I'll do that.
5 minutes. So now your job is to sit here and take care of everything.
Yeah, if you want to.
Yeah, up to you.
Maybe I can.
But first of all, you should know he will start 10:10.
Yeah,
right?
yeah.
So you have to change everything now to keep
It's
track.
okay, we have 1 hour for lunch, maybe then we have to.
We are
Yeah,
only
I will
10 minutes late.
Yeah.
So the lunch
Okay.
will wait for
That's
10
good.
minutes?
Yeah.
So, but you have to change this to
Yeah.
10, 10,
I will,
11, 10, 11:40, and
Increments,
yeah,
yes.
and
It's
keep
okay.
track.
And then.
Yeah.
Ja, det börjar nu efter på grunden och igenom dig.
Bonjour, ça va?
Ouais.
Tu veux faire le share screen?
I just, because I'm using my ECMWF laptop, I struggle to share my screen at the minute because you're recording and the laptop is not happy. But I will find a solution.
I wonder what should we do there? No.
Okay, still have 10 minutes.
Yeah, that's good.
5.
Yeah. So no, just coffee here. Okay. And then Wednesday, break, lunch, break.
Is nothing ordered?
No.
That's okay. To take the day we take last day we had anything.
Okay, I think we need
Yeah.
the person because she was supposed to handle all of this.
Okay.
I think I need to leave Zoom, change the permissions, and join again. I'll do that.
Yeah, then you log out and log in again. Yeah.
Yeah, exactly. Yeah, see you in a bit.
I will check what we have.
Okay.
here.
Yeah, because I want something of the signage to bring. Yeah. Because it would be better like, we go back to Bergen and then.
We will check with
Can you please? And then here, we need to have dinner at 7. It says 6:30, but.
Oh, 7.
Wednesday.
Yeah, that's okay.
There's so many breaks here.
Yeah.
If you can just let us know, if you can just put it in, if you just write here, or they send us an email or whatever.
And I'm leaving for the guys I want.
Yeah, I will stay here. And for the posters, if you want, we can start setting up posters. Because, we have some this here, and you can only use.
He's saying that R
wooden bar.
is full.
Yeah, the wooden bars.
Was epsilon
I mean, whatever.
A, epsilon B.
Mhm.
Transport, yeah?
That's full, yeah.
And epsilon A is the
It's the,
Y minus X.
the ops minus forecast.
No,
Yeah.
this is the unlike one, and then
Yeah.
XB.
The truth,
XB is the Y minus X forecast or truth.
Yeah.
I don't know, because it doesn't know the truth, so it's forecast.
Yeah.
So basically, is making a full R matrix by looking at the innovations in analyze and in the forecast.
Yeah.
But these two, I mean, I don't know, I don't remember anymore.
There was, yeah.
But these two are really basically are how to say intrinsically depends on how EnKF it's updated to XA.
Yeah, but I think that's not what he had in the equation. It's he's really using what the De Rosier 2005 paper is doing. See, there's a target R, which is the true.
So you talk about targeting observations.
Yeah.
I have a cake for you. I think I only use the wooden bar, okay? Not on the wall because they don't want that.
I still have some issues to share my screen. I'm working on that.
Yeah, or you want to send your slides to Randy and Chalong? Randy, is it your laptop? Is it your laptop or is it Xiaodong's laptop? Yeah. It's a sharing screen on the corporate computers.
So they are not
He's working on it.
able to?
Yeah, still working on it.
Oh. You know what? This is Zoom. And then can
Yep. Could
So
you
it's the-
would you mind to stop the recording?
For having me. And yeah, happy to be here. And first of all, I want to thank my co-workers who helped creating this presentation. So yeah, Jesper, who is here with me, and Henrik and Henrik. We're all from DHIAS Denmark, and I'm now presenting a sort of case study where we combine machine learning and data assimilation to improve hydrodynamic forecasting in the tidal estuary. So some background and motivation. Our area of interest is actually one of our clients, so the Port of Hamburg, which is located in northern Germany, in the city of Hamburg, obviously, between the North and the Baltic Sea. And it's the largest seaport in Germany, and it's the second largest in Europe, as far as I know, and in the top 20 in the world. And of course, for such a port, it's vital to German economy, and it's important to ensure navigability. Yeah. I hope you could understand me well before, but it's might even be better now. So it's important to ensure navigability, nautical safety, and of course the efficiency in port operations. Nobody wants to waste too much money. And for this, it's really useful to have a decent knowledge of hydraulic conditions in the Elbe estuary here. So in terms of nautical navigation, our clients might need information of bridge passage heights so that containers don't get knocked down from container ships. Under keel clearance, the same, but with the ground so that ships don't run aground. We have a small picture here on the bottom left. That's under keel clearance. For accident investigation, the current speeds are vital. And for, in the longer term, reduction of maintenance, for example, dredging. So right now we're actually operating a model, and it's a numerical model of the Elbe estuary, which you can see in the map here. It's approximately 50 kilometers in width, covering a decent part of the Elbe River around the port of Hamburg. It's two-dimensional, as I've said, and it's implemented in our own software, EnKF. It's a real-time model which has been in operation for approximately 10 years with incremental upgrades every now and then. What we do in this model is we do a hindcast of 1.5 hours, so where we actually have measurements and all the boundary conditions we need to run the model, and then we do a forecast of 8.5 hours to make a prediction of the hydrodynamic conditions in the Elbe estuary around the port of Hamburg. And the model runs are updated hourly with these hindcasts and forecasts. So which sort of data goes into our model? The boundary conditions, which are really driving this model. So on the downstream top left here, we include a water level boundary condition. And this, for hindcast, we actually can obtain the measurements in almost real time. But for the forecast, we have to rely on an external prediction. And on the upstream boundary condition, so to the bottom right, we apply discharge. And to forecast this, we just use naive or persistent forecasting, just taking the last known value and extrapolating that into the future. So quite simple, but we can see that the temporal variability of these both boundary conditions varies a lot. So discharge is actually not that variable. Further model parameterization is, for instance, bat resistance. We can also say that we consider dynamic wetting and drying of tidal flats, for instance. So the model is actually expanding and collapsing in areas which get flooded and then dry out during such a tidal cycle. The currently known problems in our analysis and also analysis of our client shows quite strong uncertainty in the externally provided water level boundary forecasts. And of course, we have further uncertainty in model parameterization. For instance, we do not include meteorological forcings right now. We just use a yearly average bathymetry, so the geometry of the river might actually, in fact, is subject to change throughout the course of 1 year. And of course, roughness and the overall geometry are also quite coarsely parameterized. So how good or bad is our model actually? Let's do a quick assessment of the model skill. And for this, of course, we need observations. Lucky for us, the Elbe River is actually quite well measured, observed river. We will be focusing on water level observations in this talk, but we also would be able to access currents, discharge, wind, or even suspended sediment concentrations and turbidity. And we can see here 2 measurement stations. On the left, we see in blue just tidal water level fluctuations and the current speeds along with them. And on the right-hand side, we can see the wind speed and direction at another gauge. So how do we assess the model skill right now? We just sample from 1 year and do predictions. We extract 100 samples throughout the year 2016 and then let the model run. So we initialize the forecast where we are mainly interested in with the hindcast where we still have access to all the measured values. And for the forecast, we forecast the water level boundary conditions with an autoregressive process, which mimics the externally provided data we are actually getting. We haven't disregarded the externally provided, but we mimic this, the accuracy of the externally provided with an autoregressive model. And the Q, the discharge, is persistent as in the operational model. So we do a forecast of 9 hours for each of these samples. And we are evaluating here the unbiased root mean square error. So just subtracting the mean from the RMSE. And what we are seeing here in the bar plot is just an all samples average. So this contains 100 samples throughout the year. We sample, I should have said that earlier, in 85 hours distant time steps. So we are not always sampling the same times of the day, but the times of the day for our samples actually vary. So, and what do we see at this exemplarily picked observation station, Seemanshaft, here? We can see that the error, as expected, increases with lead time. So we start out with a 8.3 centimeters uncertainty in predicted water levels, and then steadily increasing up to like 13 centimeters. And you can also see the dashed line in the plot. And this is just for reference. This is a hindcast. We run the model for the entire year of 2016 with all observations existing for the model. So this would be the perfect case, the reference case. And yeah, as it is obvious, for the first hour of lead time, we can mesh the reference case quite well, but then our model quality decays with forecast time. So how to improve the operational model? First thing would be to provide decent initial conditions, better initial conditions by means of data assimilation. So data assimilation, well, as everyone here knows, allows for the continuous update with observations, and of course useful is also the model skill assessment, which we can do continuously, and then spatial and multivariate propagation of information and a physically consistent representation. So for the first phase of this talk, we'll be focusing to improve the hindcast, to improve initial conditions for our forecast model, and see what this brings us. So our assimilation setups, we are using a serial ensemble Kalman filter. We're applying temporal smoothing, no localization. We're creating an ensemble with 10 members. I hope it's visible. You can see the ensemble mean of the surface elevation and then the different members depicted on the bottom right, close to the boundary condition. And we do this by perturbing the water level boundary condition in magnitude. Yeah, and the temporal propagation of the perturbations, we do this by an autoregressive first order process with a half-life here of 3 hours. And this all this, yeah, sampled from a Gaussian with a standard deviation of 0.2 meters. And we can also say that we use two stations depicted here in blue for assimilation. These have been found suitable after a couple of tests, and we use 3 stations for validation, of which I'm showing just one in this talk. So first results with data assimilation. We can see here, for reference, the free model we've seen before, as it is in the operational model, and we can see what's to be expected. Well, the data assimilation in the first time step, first hour of forecasting, actually halves the error. So this is quite a significant improvement. However, a bit as expected, it decays over time, and after 4 hours, it's just yeah, identical to our free run without improved initial conditions by data assimilation. So we see the reversion to non-data assimilated forecasts, which of course is to be expected. For reference, we can also see that we did a free run, the yellow dashed line. This is the hindcast with data assimilation active over 1 year. So this would be the reference, of course, for all lead times if we had all observations of the future, which is not possible. So we can overall say that due to this fast decaying effect of data assimilation, we have a dynamic system which is strongly driven by boundary conditions. And to improve the long-term forecast, better future observations for assimilation would be nice. So providing future observations for data assimilation, we try this with a machine learning approach. Why do we do this? Because it's suited for fast time series forecasting, which is vital to an operational system. suited for prediction here. It's easy to consider features from more distant gauges, and I've added a small video here of the North Sea, and then in red, maybe in observations we might want to take into account for a machine learning model as a feature, and then the yellow arrow points to a station we might actually predict. So we get a bit of lead time on the information, which is propagated our way. We can also easily consider other features which are not included in our numerical model. And these might be learned and then considered by the data-driven model. For example, one could think of seasonal vegetation, which is not parameterized in the model, but might lead to varying bat resistance over the course of 1 year. So best case, and I know this is arguably might be wrong, but it could be easy to set up, and with little calibration, we might get decent results for forecasting 2 water level gauges. It's not a super complicated problem. And I know tweaking of parameters and hyperparameters of a machine learning model can take ages, but we're quite optimistic that this might be an easy way. So predicting water levels at assimilation stations, which are function of wind speeds and directions in the North Sea, upstream discharge, and water levels of neighboring stations, which implicitly include, of course, maybe information about bat resistance when we look at the propagation between 2 adjacent stations. Also meteorological conditions like barotropic pressure and so on. So these might be the features we want to include in a model. And here we use the long short-term memory model. We use this for its ability to input and output sequences, of course, but also for its ability to learn long-term features and correlations. And on the bottom left, we have some exemplary input features. These are not used in the final, not only the ones used in the final model, but we use them for a brief first test run. So water level in the North Sea, water level in the Elbe, and then the discharge. And we came up with this very quick run, but also decent results. All in all, including training 1 minute, and this would cause input data. So for the final model, the long short-term memory model, what we consider after some trial and error are the water levels in the North Sea. We can see Helgoland on the top left here, and Cuxhaven, which is on the mouth of the Elbe estuary. So we were expecting some lead time for the tides until they reach the Hamburg port area. This might be useful. We are considering wind speed in Cuxhaven as well. And we're considering discharge on the upstream boundary condition in our data, we can see on the bottom left. And of course, we consider temporal features such as hour of the day and day of the year. For training and validation, we use the years 2017 until 2019. We split it 80-20 between training and validation. So the model topology and settings, we input 12 lagged hours of features, each time 5 minutes time steps, so 144 values in a sequence we input. And then we have 2 LSTM layers with 265 and 128 units, and we have an output dense layer also for 12 lead hours. So the hybrid model setups, just to recap, data assimilation allows us for the continuous update of the observations and the spatial and multivariate propagation, which is really important here. We don't have that from the ML time series prediction. And the ML, on the other hand, allows for fast time series forecasting and really taking into account features outside of the model domain. So we hope all in all that combining forecasts with different uncertainties from the deterministic numerical model and from the machine learning model will lead to smaller overall uncertainty. So these are some final results from training the LSTM model. So we are predicting, also to recap, the assimilation stations Blankenese and Schöpfstelle And we can see here 2 random draws from the all the samples we created, the 100 samples over the year for predictions. So we can see in black the hindpass and in blue the predicted LSTM predicted values, and then in red on the right hand side the errors. This of course can be evaluated in a condensed manner and also evaluating all of the 100 samples. We can see the errors of the pure long short-term memory forecast. It's very reliable for short lead times. So I would say, well, we have in mind the errors of the numerical model until 5 to 6 hours, it's more reliable. Then we can also see that the errors explode for 8 and 9 hours, a bit more than in the numerical model. And if we see that we actually get larger errors with the LSTM for longer lead times, we consider this by decreasing our certainty of these artificial observations in the forecast by increasing the standard deviation for the measurement error of those over time. So we say small lead times here depicted in purple, and on the right hand side you have a small standard deviation of 0.2, and then we increase that to 0.6. So some results. Now we have all the results in one place. We can see the gray model as is, our operational model, the gray bars. We can see the one in yellow where we provided the initial conditions from a data assimilation model, which is good for first hour lead time, but then quickly decays in prediction quality, accuracy. In light green, you can see a data assimilation LSTM combined hybrid model with a constant standard deviations on the measurement errors of 0.2. And in dark green, we can see the model with an increasing variable standard deviation, so less trust in future observations. What we can see here is that in up to a lead time of 7 hours, the LSTM models do better. We can also see that the variable standard deviation did not substantially increase model results here up to quite long lead times, but we can see that with a lead time of 9 hours, it gets beneficial to put less trust on the LSTM. So some summary and outlook. So we looked at a combination of data-driven forecasts and a numerical model with data assimilation. And we can say that the overall forecast quality improved quite a lot. And so we can see that it's worth to combine time series forecasting and data assimilation, for a physically consistent multivariate representation. But future work is needed. I think these are just the first results for us really to prove our point. And so the evaluation of other variables, we have a multivariate propagation of information. So current speeds, discharge, how do they improve by just assimilating for water level observations like we did here? This would be a next step. Improving the LSTM time series predictions. We could see that I've just used 2 years of training data, which is not a lot considering the complexity of the system. This should be improved, but of course it takes some preparation. And this would also improve the prediction of rare and extreme events. Yeah. And that's it. Thanks.
Thank you, Clemens. We have questions from the room. Yes. Wait, microphone's coming.
Very interesting work. So I think your argument is convincing in that you use LSTM to provide some artificial observations. But I thought that I was expecting that you're just using that to predict the boundary condition at the entrance, but then you're trying to overreach into the interior domain to provide artificial observations. As you go further to the you're training from the outside, right, of the domain, and then as you reach into the river, your correlation is weaker and weaker, right? So I don't understand why do you need artificial observations from a like a time series model? Wouldn't it be better just limit the machine learning to the inlet?
Of course, we also, this would also be a step to add, and we thought about that. Also forecasting the boundary condition with an LSTM model. I think you're right, but nonetheless, we saw that also the initial conditions where we had perfect knowledge of the boundary conditions, where we had all the observations, data assimilation actually improved by the model quality in the first lead hour by 50%. So it's still worth to consider data assimilation on these assimilation stations, but it would also definitely be worth to include in the LSTM forecast the boundary condition, and this is our long-term idea to have more or less redundant systems for forecasting the boundary conditions. And then of course the other forecast is more physically based, so it could catch large errors of the LSTM model. But this also regarding the assimilation, the good thing is that we actually have we can do an intersection of the physical model and the LSTM forecast and put different types of trust on each of these. And for the boundary condition, large errors in the LSTM model, which occur, of course, in extreme events also, would propagate through the entire system, and we need to make it more robust, I think, in that sense. But yeah, very good point, I guess.
Another question?
Hi. I hope so. Great talk. I actually want to continue on that question beforehand. So first, I want to confirm that did I understand correctly that when you're looking at the time series, so you're basing it on existing. So for example, if you now, when you're creating that time series, you're saying that if we now have a certain condition in Northern Sea, 6 hours from this, it will have in real time this.
Yeah.
Just want to confirm that because I often get things wrong. But because you got that, I was like, or what's your answer on that? Because if you're thinking about the intersectionality, so you're basically thinking like if you have your physical model and you use those driver conditions there to do something, and then you use the artificial observation, wouldn't you in that situation be using, if you're talking about using it at the same time, wouldn't you be using the same data point multiple times for one observation? Or sorry, wouldn't you be calculating multiple observations from one observation in that case?
I'm not sure I get the question entirely.
I'm bad at that question. So I mean is that when you're setting so I just want to confirm if I understood. So as he said that there's a time series, so 12 sets of different time series, and then he said that you're considering using like the insight so that you have a dynamical model where you have the boundary conditions that you get from it, and then you have the artificial observations. And then you were, if I understood correctly, you're talking about using those at the same time, but wouldn't you then be using the information from one data point multiple times in the assimilation?
So very good question. Yeah, I guess that's something to consider. I have to really get my head around it, but we have lunch soon, so.
Maybe a very quick question. Did you compare your hybrid model with purely time series prediction?
I had the time series error included on the early slides. So yeah, we actually saw that the pure time series forecasting is quite good, but of course we don't have that spatial representation, and this is the main point. So our client and they need that spatial information to really know the current speeds everywhere, and this is of course much harder to do. So we are using data assimilation for this physically consistent spatial interpolation, so to speak. Yeah.
Thanks.
Thanks. Yeah.